Okay, can I be heard? Yes, cool. So this is a second talk about automatic differentiation, and instead of, I guess, decomposing reverse ID as forward mode plus separate steps, I'm going to do this as a whole, as a monolith thing, but describing it as an optimization process from a simple algorithm to a more complicated algorithm. So for the people that didn't see the previous talk, I guess also online, automatic differentiation, very briefly, is the study of differentiating expressions, which we learned in high school, except that if you have more complicated expressions with programming language constructs, maybe control flow, data structures, etc., you might not be sure what exactly to do here, and AD is basically a way or a collection of rules or a variety of collections of rules that let you differentiate these kinds of things. And in particular, the goal is to do this efficiently in some sense, which I will explain more on a later slide. So this talk is, we start with a very naive but quite beautiful, which is subjective, code transformation which does reverse AD on a purely functional language. And we optimize this using semantics preserving optimizations to an algorithm that can do efficient reverse AD on a subset of Haskell 98, a decently large subset. And the optimizations that we perform are threefold. The first one is the application of a distributive law, which occurs in other kinds of reverse AD implementations. And we do this by staging certain function calls, which I will explain later. The second and the third, which are the application of sparse vectors and mutable arrays, are fairly standard functional programming optimizations, which also apply to lots of other algorithms, especially in functional AD. There are two papers that I would like to call out. One is from POPL 3 years ago by Brunel, Mazza and Pagani, who analyzed this initial naive transformation and gave an operational semantics for it that allowed the transformation to produce efficient code. In this paper, instead of giving a different semantics, we work in the standard call by value semantics and instead give optimizations that in that semantics produce something efficient. Another paper was presented last year at POPL by Kravets and co-authors, who gave a very similar development, but it was actually presented sufficiently differently that this is still somewhat of a new story. So again, another background slide just about forward and reverse mode AD, because both compute the derivative, but really the difference is what they do efficiently. Forward mode works well if your function has one input and returns many outputs, whereas reverse AD works well if you have many inputs and return only one output. Where efficiently here is with a constant factor overhead in time over the original program. So because reverse AD is by far the most common case, that is the one we look at. For example, in machine learning, you have many parameters. In statistical inference, you have many parameters, etc. So the method we are looking at is, the style we're looking at is dual numbers AD. So what is dual numbers AD? Consider the original program on the left top of the slide, which is a simple program that takes two real scalars as input, adds them together, multiplies x to that result, and then returns w. So in forward mode dual numbers AD, which is one of the most well-known forms of automatic differentiation, you pair up every real scalar with the second real scalar that in some sense encodes the sensitivity of this value with respect to some earlier value, some unspecified earlier value. And these sensitivities you can then propagate through the program using the standard differentiation rules from high school, basically, including the chain rule. And this allows you to compute the corresponding sensitivity for the program result. In reverse AD, there is typically some form of inversion of control flow going on. And here it is the same. So if you want to do reverse AD in this dual number style, where you just modify the real scalars to be some pair of things, the thing you pair with it is not a simple real scalar, but instead a backpropagator. This is a function. Just the notation here, the lollipop is a linear function arrow, which is an algebraically linear function arrow. So operationally, this is just a function. It's just that it happens to be linear, which is useful for reasoning about the algorithm. And the underlined R's are simply R's. I'm just emphasizing that I'm using the vector space interpretation of R. And what you see here is that these functions are being called here. So aside from the fact that I hope you can see that there's a nice correspondence between the forward AD and the reverse AD version, you can syntactically see that there's lots of correspondences. If you call dw, then you will be calling dz and dx, which will be calling dx and dy, and so you move sort of backwards through the program. So let us see how you can define this code transformation, because this is the first one. Let's first look at the transformation on types. So on basically all types except the actual real scalar type, the type transformation doesn't really do anything. It's just structurally recursive. The only place where it does something is for real scalars, where it maps it to the familiar pair from the previous slide. And this C type is the top-level input type, which is the type of the final gradient that we are going to produce. And the whole transformation is parametrically polymorphic in this type C, hence I'm writing it here as a parameter. So for example, just to hammer this point home that it's really structurally recursive, if the original program for some reason contained this wild type, then mapping DC over this simply replaces the real scalars with the pairs of forward AD or reverse AD. In our case, reverse AD. So let's look at the transformation on terms. Remember that we're looking at a pure functional language. So at the top of the slide in gray, there is a reminder of the type transformation. Again, for most term formers in our language, the transformation is just structurally recursive. It doesn't do anything. The only interesting action is when you do something non-trivial with the real scalars, which is when you're doing some arithmetic. So for example, for multiplication, you compute, the pairs corresponding to the arguments of the multiplication, and then in the pair you return the primal result, which is simply the multiplication of the original results from the arguments, and the backpropagator that you create takes in this sort of reverse sensitivity corresponding to the result of the multiplication, and then you call the backpropagators of the arguments at this value d multiplied by the partial derivative of multiplication with respect to the two arguments. In this case, that looks like this, and this generalizes to all other simple arithmetic operations. Question is this fast? And the answer is, of course, no. So if we look at the same original program, which I'll call T, if you look at the data flow graph of that program, you see that x and y compute z, and then x and z compute w. This is fine. Then looking at the dual numbers reverse AD transformed version of this program, and focusing only on the call structure of the backpropagators, you see that the call graph that you get is naturally the opposite graph of the data flow graph of the original program. This is natural given how we designed the algorithm. However, function calls are not anything special. They just do their thing. They don't sort of naturally deduplicate. So if you don't watch out, basically what you get is some sort of exponential explosion of call graphs to get something that doesn't fit on the slide anymore. So we need to fix this. And the optimization that we're going to use to fix this is linear factoring, which is heavily inspired by Brunel, Mazza and Pagani from 3 years ago. So recall that these backpropagators are algebraically linear functions, which means that they preserve zero addition and scalar multiplication. Further note that the backpropagators have the real scalar, the real numbers as their domain, which means that each such function can really be written as just a scalar multiple of some static vector. There's a linear algebra argument you can make here. And this means that you can expand the second property of linear functions into something involving that vector v, where if you call this function f twice at different arguments and add the results, then this is really similar to doing some operations on vectors. And the equality in the middle is really some kind of distributive law between scalar multiplication and addition. And I hope it is clear that the expression on the right is cheaper, because R and S are simply real numbers and adding them is cheap, whereas the scalar multiplication is very expensive, especially if this vector v is very long. So I was talking about the distributive law, but usually when you want to apply a distributive law, the question is, where do you apply it? How do you know where to apply it? And how do you even get the program to apply it at the places where you want it to be applied? So let us first look at where we want it to be applied. So we look at evaluation orders. So we step out of the standard call by value evaluation order here. This is the same program as before, and this is the same call graph of the backpropagators as before, except I'm now assuming that x and y were actually the results of some earlier computation, which I'm eliding. So that means that dx and dy also call some earlier backpropagators that I'm eliding. And in general, because we're talking about reverse AD, we're getting some sort of inversion of control flow, so we expect the evaluation order here to be, in some sense, the reverse of the forward pass evaluation order. So give x and y some values, and then we can start the evaluation order. Let's just see what happens. So we start by calling dw at 1, and this call we must expand. We have nothing else to do. We get a call to dx, and we get a call to dz. So assume that we now choose to call dz. Either choice is semantically valid. Expanding the call to dz produces a call to dx and a call to dy. And now we can do this linear factoring, the distributive law, to take together the two calls to dx to produce one single call to dx. Then evaluating further the two calls, we get, well, the etc1, the etc2 calls as usual. In an alternate universe, through the black hole, I guess, we could also have made a different choice here. We could have called dx first, in which case we got, well, the elided calls on the left, and then calling dz and then dx and then dy, because that's the only real thing we can do. We end up with this situation where we got the calls to the etc1 calls twice. And this is a bad thing, because you might think that we can now still take these together, maybe, using linear factoring, but I hope it is clear that you cannot wait too long. You must do it early enough, because otherwise you get the same explosion that we were talking about. The question is, in this situation, because here it is really the place where you must make this decision, which is the right one, and how do you know which is the right one? And the answer can be found in the fact that we must use the reverse of the forward pass evaluation order. So let us give all the backpropagators some IDs, monotonically increasing in the order in which we create them. So these IDs precisely follow the forward pass evaluation order, where in this case I've assumed that y was computed first, then x was computed, then z, and then w. And now you see that if you follow this mantra, you see that you must simply evaluate the call with the highest ID first, because that cannot produce any calls to backpropagators with higher IDs, because those weren't created at the point where this backpropagator was created. So we indeed see that on our side of the universe, we make the right choice, and in the alternate universe, the wrong choice was made. It should be mentioned that this particular evaluation order is not the only one that produces the right complexity, but it is a nicely principled one, and it is one that's decently implementable. So what do we need to do? We need to number the backpropagators in the forward pass so that we can do this. And we need to call them incrementally in decreasing order of IDs to get this to work. And to do this incremental calling, we need to stage the function call so that we have some control over in which order they are evaluated. And there's a problem with which kind of came and went, which is that if you want to take together calls to the same function, you must somehow see that these are calls to the same function, so you must have equality in functions, which is a problem. However, the functions now have IDs, so we can compare the IDs instead, so all is good. So these are the two things that we need to do. Firstly, to number the backpropagators in the forward pass, we are going to change the target program to monadic code. And this is not very complicated. I'll just show the type transformation here and the turn transformation you can see in the paper. We're going to number the backpropagators, so we should insert this in somewhere. And we are going to change the transformation of function arrows to, a state monad over int, so that we can generate the IDs. This works fine. And to stage the function calls, we are going to change the codomain of our backpropagators from a value c, which was this top-level gradient, to a computation that will produce a c, which we can then evaluate. And this computation we represent as a staged c, which is some representation of a term that I show on the bottom of the slide. What I should note here is that there is still a constant c because we need to inject one-hot values at some point, and this map is keyed by the IDs of the backpropagators. The details I cannot really cover in this time. So this fixes this problem. However, there are still some other issues that we need to solve. So let us look at the transformation for primitive operations, which is, I'm skipping now this staging of function calls, but that's sort of an orthogonal thing. It works in combination. The problem is that this plus over here is a plus on values of type C, and this 0 over here is a value of type C. But C was the top level input type, and by assumption of reverse ID, that's going to be very large. So these operations are very expensive, much more expensive than the primal operations they correspond to, so this is bad. How do we fix this? We fix this using sparse vectors, and one that works, it turns out to work very well, is a simple Cayley transformation, which is known to functional programmers as the difference list trick, where you change a monoid into the monoid of endomorphisms on that monoid, or you can see this as an action of the monoid on itself, where the 0 turns into the identity function and the plus turns into function composition. And you can go back and you end up in the same place where you started. Why do we do this? Well, because 0 and plus have now become very cheap. Because the identity function is just a value which you can allocate in constant time, and function composition is just the allocation of a closure in constant time, so that's very cheap. How do we apply this? We change the codomain of our backpropagators from stage C to stage C arrow stage C. And if you work this through the transformation, you need to change very little, and everything just works. The last thing that we need to do is that we still have some lingering complexity issues. One is fairly obvious in that this map that we have over here, which is naturally a fairly simple tree map in standard pure functional programming, this incurs log factors in our complexity. And because these keys are the IDs of the backpropagators, which are monotonically increasing IDs starting from 0 sequentially, the obvious thing is to replace this with an array. Which you can do using, for example, local state threads in the style of the Haskell SD monad, or resource linear types, also called substructurally linear types. And this works fine. And the last thing that we need to change is that this constant here of type C, what we do with this wasn't really apparent in this presentation because I was skipping the wrapper that goes around this whole transformation. But the only values that actually get put in here are one-hot values. So everything is 0 except for one scalar. And those are all added together. So what we really want is to be able to do sort of point updates on this value in constant time. So we simply change this to an array containing just the scalars in C. And the actual structure, we are just going to sort of route around the algorithm to merge back with the gradient in the end, and it turns out that this works perfectly fine. And now the joke, really, is that if you look at this representation, and you defunctionalize these backpropagators, which is not very hard because there's just a few forms, those backpropagators will contain precisely the partial derivatives of your operations in the primal pass, in the forward pass. And these derivative values, the r's on the right-hand side of the slide, get nicely filled in the reverse pass, which are the derivatives of the primal operations. So you really have created taping, which has been known as a working AD algorithm for decades, basically. And we have derived this from a fairly nice algorithm, which is very easy for reverse AD algorithms to prove correct using a variety of methods. And we have transformed this using semantics preserving optimizations to a thing that's actually decently efficient. We have an implementation of this that is implemented in template Haskell, and which you can find in the paper. Thank you.
Thank you, Tom. We have time to take a few questions.
Hi, Mike Lawrence from Relational AI. So at 2 points, you used some information from the forward run of the program to solve problems. Like you used you reverse the order that you evaluate things to find the right order to unfold things.
Sorry, it's.
Can you hear me?
Hard. Thank you.
You reversed the order that you evaluated things in the forward pass to figure out the order to unfold things in the reverse pass to apply to the distributive laws. And you also used IDs assigned based on when things were called to figure out when functions were equal and when you could distribute. Could there be a better order than the reverse order to evaluate things in? And could you gain more efficiency if you could identify when you called the same function, even if it wasn't at the same time?
I could not hear every word that you said, but at least I can answer the question about whether there is another order that might or might not be more efficient. And I think there cannot be, because, or at least not in every case. Because in the worst case, for some reverse ID algorithm, you cannot really do better than letting the reverse pass take on the order of magnitude equally long as the forward pass. And the same kind of holds for the space complexity. You have to use the same amount of space as the runtime of the forward pass. So you might be able to skip some backpropagator invocations in some cases, but you will not be able to actually improve any kind of worst case complexity. I hope that answers your question.
I will also take the opportunity to ask one question. So you derived a more efficient implementation of reverse mode AD, but I didn't see any numbers. Have you compared actually your implementation versus other implementation?
Right. So I don't think I can claim that this is really a more efficient implementation necessarily, if anything.
Well, you have this efficient on your slide.
Right. So okay. So what this efficient refers to is that firstly, the complexity is the complexity that you expect, and it is the optimal complexity, because you can't really do any better, though I'm not aware of any proof that lower bound. But aside from the complexity, we did compare our implementation with Edward Kmet's library called AD, which is on Hackage of Haskell. And I think in our reasonably limited tests, we were up to twice as slow as that library, which, given that this is mostly a theoretical development, and I did not optimize the implementation at all, seems at least like a validation that this is not a wildly inefficient thing. It actually has the potential to do sort of the right thing.
Yeah, okay. Yeah, let's thank Tom again.